So we're going to talk to two of the three laws that are on our formula sheet. There's also one regarding independent events. We'll talk about independent events in a little bit of time. But conditional probability, we've been through that law. The probability addition law, and again that makes a little bit of sense when you think about our Venn diagrams. We're double counting this middle section if we add up PA and PB. So we have to subtract one of those because we've double counted it. Does that make sense? So if we're PA, in this example, right, how many people are Good Samaritans? 25. How many people, tell everyone they're Good Samaritans? 20. If we added PA and PB up, so we have 25 plus 20, we'd have 45 people involved in that part there, correct? But in reality, there's 23 plus 2 plus 18, which is... So PA and PB, if we do that, we double count the middle section, so we have to subtract one round of the middle section. Cool? So that's the probability addition law. Really, really important that we remember these rules can be, what can we do with these rules? So say I'm asked for, I don't know, P, A and B, what should I do? Start. What was that? I need to start with R. Rearrange to isolate the variable that I actually want. Cool? So just because this is an addition law with the U, B there, I can find any one of these values providing I've got the other three. Awesome. And I will leave you to ponder that whilst we go through and do, you'll need to use both these equations. It is known that, I left the square up from the other day. I forgot to ask you, there's a distractor in this question. What's the distractor that isn't actually helpful in solving the question? Oh, 50 people, you're also brilliant. Yeah, you don't care how many people, it's purely about probability in this situation. Cool, whereas in this one, what do I have to do with the number of people? Turn those into probability. So in that case, the total number does matter. But here we go, you guys can start with that. I'll give you 5 seconds while I go and find my markers. So for A, what rule am I using? The addition rule. So I'll get us to write the addition rule out and then substitute in the next line, substitute in all our values. We've got 0.4. Very good. We needed that for question B. How convenient. So now we need to use our known values to find the probability of A given the probability of B. Might do it underneath instead. You got 0.8? Very good. So it feels they're sort of getting a grasp of conditional probability. We would like more than one more practice before we go off and do individual. Okay, we'll do one more on the board for those who want to do it, otherwise we can move off and do some individual stuff. So we're going to look at another example of conditional probability. This one's a little bit different. Why? Venn diagram, and we also haven't been given the probabilities, we have to determine those ourselves. So here is the situation. G represents the number of people that are actually good Samaritans, so people that do the right thing for the right reasons. T represents the people that tell people that they're good Samaritans. And we're looking at the relationship between people telling you that they're good Samaritans versus the reality that they are actually good Samaritans. Oh, I've lost my little hash. So the first thing I want us to do is to represent this as a probability two-way table. Should have added one more, and it's going to be some gross numbers. Your virtues they cast in water, your sins they cast in stone. Cool. So I just added the total and divided each of those terms. I'm going to leave them in fraction form because I didn't give us a nice gentle number. I should have done like over 50, but I didn't. So determine the probability that someone who says they are a good Samaritan actually is one. So I'll let you fill out the formula first of all. So what do we know about this person? This hypothetical person. What do we know about this hypothetical person? No. We don't know if they're a good Samaritan. We know that they say they're a good Samaritan. So what the probability goes, what are we putting in the second part of this conditional probability formula? We know that they are definitely T. The person that we are dealing with is definitely someone who tells us that they are a good Samaritan. What do we want to know? The probability that they actually are a good Samaritan. So we would write G given T, which is the probability of G and T divided by the probability of T. So 2 over 20 or 1 over 10, which is 0.1. So what is that telling us? There is a 10% chance that the person telling us they're a good Samaritan actually is, which means there is a 90% chance that the person telling us they're a good Samaritan is not. Hypotheticals purely. Let's say, as a second example, I'll do it, where do we do it? I'll do it over where I've done my working over here. The question C, let's say I see someone with a donkey and a man draped over it. What's the probability I see a person doing a good deed with no thought of, I'm just going to say helping a needy member. I don't know. Helping out the brekkie van maybe. What's the probability that they are not going to tell people about that? Or refer to oneself as a good Samaritan? Equation first of all, the probability that not T, given that we know that they are G. Again, we go back to that formula. We're going to get sick of doing it, but eventually it'll sink in. Who thinks that fractions make this a little bit easier sometimes? You can see why the fractions made this question particularly quite easy. What could I do with the 59s? So it becomes 2 over 10, correct? 2 over 20, thank you. Your actions they write in, your virtues they write in water, your sins they cut. I'll keep saying it. Fractions are our friends, very good.
Don't speak to me, please.
So there is a 92% chance that someone is doing the right thing for the right reasons, won't feel the need to spruik or talk about it. Sweet. Are we happy with that? Exercise, we're not going to have much time. You can